So to remind you, we're going to ordinary symmetries. And from symmetry group G, we can associate some conserved current J. And in the Euclidean picture, this gives us what we call the symmetry defect operator. That's topological. Right, so that means that essentially this is independent under deformations of sigma. We say D minus one dimensional closed hole. And there was one other thing I wanted to say about this, is that it might be obvious from all the equations we've written earlier, but it's important that these symmetry defect operators obey a group law. There we go. Okay. So now I wanted to talk about another thing that we often do when we're analyzing symmetries in a theory, is that we often also can utilize the notion of a background gauge field. So what this is it's like Apple.
Sorry to come back to that a little bit, but maybe I'm mixing up things, but normally you say that something is dependent on deformations.
Yeah.
Don't they require some kind of flatness condition, that the curvature related to this kind of being, to this curve being zero or something like that? Or is it the conservation enough?
The conservation is enough for this to be topological, even on like curved spacetime.
Okay. So you don't need flatness.
Yeah, so the flatness condition is like, it's actually going to be, you need the background gauge field to be flat.
Okay, because it comes there.
Yeah, so if you turn on a non-trivial background for the symmetry, just like, then you can have like all sorts of weird things happen. And essentially it's because it's moving through the field. It feels, essentially the charge field feels like the magnetic charge, or the, it moves through this field and you can feel all the charge that's sort of being left behind. Right? Good. Right. Good. So turning on background gauge fields is a really nice way to probe symmetries in the quantum field theory. Right, and so what I mean by this is that so for example, let's take QED. So this is a U1 gauge theory. In other words, there's a photon we write as a vector field, mu. And there's a Dirac fermion that has charge 1. And you can write reaction for QED as, you know, I'm going to write it sort of loosely like this. So this is like the kinetic term for the photon. And then you have something that's like I psi bar d slash psi. Okay. Good. So you can think of QED as coming from free fermion theory. So free fermion theory, I psi bar psi, and gauging the symmetry psi goes to psi. Okay, so the way you do this gauging is first you add the kinetic term for the gauge field, and then you also couple a photon to the associated conserved current. So this symmetry has a conserved current that you can compute looks like sine bar gamma mu sine. And this is conserved because this is literally just zero by the equations of motion. And for free field theory, this is true as an operator equation. So the difference between what I've written here and the QED action is literally just, here's an I think, a new change. So this is sort of a funny way of writing the QED action. And it's important that you have this coupling sort of only makes sense if your associated current is conserved. Because here you're allowing for gauge transformations. So the gauge transformations for the photon are a mu goes to a mu plus derivative of lambda. And then so this term is invariant. Well, you find out essentially that this term is invariant under this gauge transformation because you get and this is 0 because J is conserved. So what I mean to turn on a background gauge field is similar to what we mean by turning on a dynamic gauge field, in that the background gauge field does not have a kinetic term, and it's not summed over in the path integral. So, table. So, and back down. So here we say A mu has kinetic term. This is no kinetic term. And here we say the path integral for QED looks like, you sum over A and you sum over psi. Okay, we're going to use Euclidean now from now on. Whereas here for a background gauge field, you don't sum over A. Rather, A has to be something that you specify. And so you think of path integral as literally being something that is has a fixed A. And so essentially the way to go from a background gauge field to a dynamical gauge field is that you can write the QED path integral as summing over A of this ZA. With the kinetic term. Okay. Very good. Cool. So this is a quick, more formal mumbo jumbo. But it actually turns out to be very useful. So the question is, why did I do this? Which is probably just going to be the refrain of all of my lectures. The reason I did it this way is that it allows us to look for anomalies. So it's good for anomalies. Okay. So let's review it for anomalies. So let's keep going with this example of QED. As we know, there's the symmetry gauge on the side. So it's the gauge symmetry. But there's also the chiral symmetry. Side. And this is only a classical symmetry. So this is a classical. So what does that mean? So that means you can define an associated current, which we're going to call gamma 5, which is classically conserved. But in the quantum field theory, the conservation equation gets corrected. You find that the divergence of the operator looks like F mu nu, F mu, epsilon mu nu, oops, I guess this is alpha beta, times some number. I'm just going to call it K. And this comes from the triangle diagram. So this is like your current JU quadrant. I guess we draw a curve like that. And this is what gives the correction to this conservation equation. And so what does that mean? What it means is that this current, the symmetry is no longer a symmetry in the quantum theory. Essentially, all of the technology we talked about last lecture doesn't work. Now this, if you tried to write a symmetry defect operator, or just any sort of charge operator, you would find that it no longer is independent of T. And in fact, it doesn't even commute with the Hamiltonian. Sorry. Yeah, I think that's true. Oh, okay. Doesn't commute with the Hamiltonian in every state. Anyways, it's not a topological operator, and so it's just not a symmetry. Your Hilbert space is not, doesn't go into representations of this charge operator. So this is a nice way of seeing the symmetry, but this is what we call an ABJ anomaly. And the reason is that you have the gauge field here. So if you have a global symmetry and two gauge symmetries here, this breaks, this sort of anomaly breaks the chiral symmetry. But more generally, you could have there are theories. For example, if you took QED with two flavors, I think there are symmetries you can write down that don't have an ABJ anomaly, but still have a cubic anomaly. So these are also called cubic anomalies because there are three corners, and it looks like a cubic polynomial. Okay, so so that was sort of a lightning review of what an ABJ anomaly is. But what's maybe more important for analyzing symmetries are called Tufts anomalies. Sorry, was there a question? So, Tufts anomalies are much more important for studying physics, at least, or it gives us more information about physics. And so this comes when you have a triangle diagram that looks like this. So if you have three currents, J1, J2, and J3, that are all global, correspond to some global symmetries. Say, for example, take U1, three copies of U1. And if there's no ABJ anomaly that breaks them, then this constitutes an anomaly. And so, essentially, the reason why it is useful to turn on background gauge fields is that the computation of this anomaly now looks much simpler. Because if you turn on a background gauge field, this doesn't become, essentially what you can do is you can replace the fact that you have a current here with the background gauge field, the photon for U1, for this U12 factor, or U13, sorry. And here you can similarly replace this for the photon for the second U1 factor. Yeah, that's right. So, so what you find essentially is if you compute, if you try to compute the divergence of the conservation equation for this J1, you find that it's violated when you turn on background gauge fields for this A2 and A3, for U12 and U13. So it's like F2, U, F3, times some integer k, or some number k. And so turning on these background gauge fields is very useful because it allows us to probe for these anomalies much more easily. Because it sort of smacks you in the face with the fact that the symmetry is violated. So this is going to be something that we return to a lot. And so it's useful to sort of write these sort of anomalies in a simpler way. So I told you if you have a partition function and you turn on a background gauge field, it now becomes a functional of the background gauge field. And I also told you that the way we couple the background gauge field to the theory is in a gauge invariant way. So if your symmetry is conserved, then it better be that the partition function is invariant under these gauge transformations. However, these Atoft anomalies are what show up when the partition function is not invariant under these gauge transformations. You find that there's some sort of phase here, which looks kind of like lambda, F nu, F alpha beta, times k. So this is our anomalous phase because here this lambda can be anything you want. And so if these were gauged, dynamical gauge fields, then you would say you have a big problem, you've broken your symmetry, but here these are background gauge fields and they're fixed. So this is just a fixed phase, and you're just saying that your partition function transforms in this way under the way you choose your background field, or rather your source. Yes?
There on the left hand side, so you said that if I replace the currents J12 and J13 with the background fields, I'll get the ABJ anomaly equation. That's the statement, right? But what happens if I don't do that? How will that anomaly manifest?
Good. So this is just something that makes this nicer. But as you were saying, I told you that there is still some sort of non-trivial diagram that tells you that there's an anomaly. And what that is it's a three-point function. So, right, so of course this is in four-dimensional theories. So it looks like a three-point function. J2 mu 1, I think this is going to be K. It's actually really messy, I think. It's a partial.
That's okay. So
Yeah, it's going to be like a delta function of x minus y. There's the next derivative. And this is going to be I think this is an alpha. Actually, it's actually sigma and beta. This is the delta of x minus z. This is the next derivative. This is an epsilon nu sigma alpha beta.
and then these replacing the currents with the background fields, that makes the anomalies easier to see.
Yeah.
That's in general using.
Yes. So in this case, it doesn't really looks like it buys. It doesn't look like it buys you anything. But there will be more complicated cases that we'll see soon, where this is sort of the only thing you can do. Because essentially the point is that here, this is a perturbative way to compute the image. We're saying that, you know, I can literally write down a Feynman diagram that tells you that this is how your partition function transforms. There's a more interesting way to compute this, in that if you turn on these background gauge fields, what you'll find is that the fermion measure has what are called zero modes. So usually when you write, you know, your functional integral d psi, I actually mean d psi times d psi of r. And to say that you have a symmetry, it tells you that for each mode here, you have the same mode here that undoes the symmetry. But when you turn on these background gauge fields, since these actually are in complex conjugate representations, or, you know, the Lorentz group or whatever, they actually don't match anymore. And so what you're finding is that this phase here is literally a variation of the difference between this minus this. And so that is that's a non-perturbative computation to show you that you have this anomaly. And that's that's a more general way to compute anomalies. Because this method only works, for example, for continuous symmetries. For discrete symmetries, this is much more complicated. Yeah.
If you sum over the ABU in order to write down the partition function, so integrating over background fields, how do you know that somehow something miraculous doesn't happen and these phases cancel the sum? Is that obvious, or is this?
So you're saying if you have these phases where the sum over A,
Yeah.
why don't these phases sort of
Is it
go?
obvious they don't?
Right. Right. So in this case, it'll actually kill the partition function entirely when you sum over A, because you're also sort of, well, okay. There's two ways you can think about it. So here I told you that you can do this integral, and I just said you sum over A. But this is defining this is also very technical. So there's sort of two options. So you can do this integral over dA in terms of the gauge invariant A's. But this only makes sense essentially for each, physical piece of data. You need to pick a representative, and then you say that it doesn't matter which one you pick, and you just do this integral. But you can only do this if this is gauge invariant, essentially. And so the other way, so that would just, if you did have this phase, I would just say, well, you're not allowed to do this. But you could tell me, I don't care. I'm just going to integrate over all possible connections, whether or not they're gauge invariant. And then you would find that for a fixed field strength F, you would sum over all of these lambdas. And that would literally, if this integral of f tilde is non-zero, then the integral of the lambda would kill it entirely. So that's I think, correct. Cool.
So,
Yes?
this is probably a very basic question. So, people typically say that if you have an anomaly, then you can reach the symmetry. But it's even more than that, right? In some sense, it's like it's even broken in the quantum theory, or not? It's more subtle than that.
Yeah, it's more subtle than that. So usually when there's an anomaly, what it means is actually that the symmetry is realized projectively on the Hilbert space. But showing that is actually very complicated. Yeah.
Okay.
and that's, okay, I just want to say that's important because as we know from quantum mechanics, the phase of a state in a partition function matters because you can have like a Berry phase, and that gives you something physical that you can measure. So I just want to say that it's not trivial to say that there's projective representation. Okay, well, since I'm talking about anomalies, I guess I might as well mention one more thing. So, again, I'm going to ask the why question. Why do we care about anomalies? What do they tell us? What does it mean? Right, and so this is important because of the renormalization group flow. So the way we think about quantum field theory is that I give you some sort of UV quantum field theory. And usually the way we say it is that there's some conformal field theory that defines the short distance behavior of your universe, if you will. And then what you can do is you add some sort of deformation, some interactions to your theory that has some scale associated to it. And then what you do is you look at what happens at the very long distance, or the low energies. And it can be that the long distance behavior is different from the short distance behavior. And the way you go from this UV description to this IR description is called the normalization group flow. So often this is totally non-trivial. We have no idea how to solve this. Given this data, how do you get this? That's generally not, we don't know. Because there can be phase transitions at intermediate energy scales. But one piece of data that we do know how to track are anomalies. So an anomaly in the UV theory, and the UV description of your theory, has to be matched by an anomaly in the IR, the long range distance of your theory. As long as this interaction didn't break the symmetry. There are sort of several ways to see that this has to be true. So the first reason why this has to match is an old argument due to Toto. And essentially what he was looking at is exactly this triangle anomaly. So imagine you have some interacting quantum field theory, and it has some fermions in it. And you have this, anomaly between three copies of U1. So there's a way that you can cancel this anomaly by adding non-interacting particles to your theory. So I just say, what you can do is you can add some fermion psi, and just say it transforms under this global symmetry. So it transforms into the U1 1 times U1 2 times U1 3. So that this plus the anomaly of this psi cancel. And now, let's see what happens in infrared. So this is my TUV, and this flows to TIR. Oops. Sorry. Also, if I need to write it larger, please tell me. I always forget because I'm standing very close, but you guys are like way back there. So anyways, this TUV flows to TIR.
So one silly question there.
Yes.
You also imagine that there's fermions. There's fermions running in that loop.
Yes.
So why do they contribute with different signs that they can?
Right. So okay. Yeah. So this since I'm dealing with three copies or three different U1, U2, U3. Three different U1 groups. This So I was saying that this is labeled by some number k that sort of tells you like the size, and it's going to be, well, it's just going to be some number k, whatever it is. So there's going to be a similar k here, which is called k psi, and it's going to be proportional to the charge of psi under each of these groups. And so you can pick the sign. You can pick these to not be positive, so that you can get a positive or negative number. And essentially, the point is you can generically pick these so that it cancels against this k. Yeah. But this psi is totally not interacting. We often call it a spectator. And since it's not interacting, it just flows to the same theory, don't it? So, right. And so since this sort of UV theory had this good global symmetry when you add these fermions, it tells you the Hilbert space is transformed perfectly well under it. And so the IR is also going to transform perfectly well. But now what it tells you is that this part of the theory has the same anomaly as the UV part did. And so in order for this full UV theory, infrared theory, to transform well under this global symmetry, this has to also have the same anomaly. And so that's one argument why the anomalies match. Or in other words, if you want to write this in terms of a partition function, okay, so say we have our UV theory, which has this partition function, and under the gauge transformations, there's the space. I'm going to just start using symbols. So what we can do is we can make some new UV theory. Which is the original UV theory times the spectator theory. And this is totally invariant. And so the point is that when this flows to the infrared, this flows to some infrared that also has to be invariant under gauge transformations. But we know that this UV theory flows to its own IR theory because these literally do not talk to each other. And this flows to itself because it's a free theory. And the only way for this theory to be invariant under gauge transformations is for these two to cancel against each other. So that's a really old argument. But I think it's also useful to have a new argument. And it comes from what's called anomaly inflow. So the idea of anomaly inflow, I'm not going to use those words right now. So imagine this is my d-dimensional spacetime, and I have my theory lives here, and I just get it at d. So we were saying that the anomalous phase looks like here's the I guess there's a k, and then there's this lambda ff tilde. And you can cancel this phase if you couple your d-dimensional theory to a d plus 1 dimensional theory. D plus 1. And we want this d plus 1 dimensional theory to have a term in it that looks like e to the I k minus sign partial mu lambda mu. Oh, shoot. Also beta epsilon. Oh, sorry. I don't want that to be. I want this to be a sigma mu alpha beta d. I guess we're working with Fourier convention, so I'm going to say this is 5. So if this term lives in your 5-dimensional theory, then this is clearly not gauge invariant because there's this boundary term. So if you look at the variation of A, which is the only term here that varies under the gauge transformation, you get e to the minus ik, or can you land a partial signal f, and then when you try to, essentially you can pull off this derivative and hit the f's with it. And since it's an anti-symmetrized, that'll be, give you a 0. But you get a boundary term. So this is M4, and this is, so this space is M4, and this is X5, which lives as M4 in its boundary. So you find is that this phase is actually going to be equal I'm just gonna, sorry. This will be a lot easier once we do different forms. Anyways, essentially this looks, the variation of this term under gauge transformations looks exactly like the anomalous phase of this Fourier theory with an opposite sign. And so that's great, except that now you've made your 4-dimensional theory a 5-dimensional theory. But I can tell you that that's okay, as long as there's no physics that happens in the bulk, in this, we call this the bulk often, in this 5-dimensional theory. So if all of your dynamics happens in the 4 dimensions, it's still a 4-dimensional theory, even though there's this imaginary 5-dimensional theory that essentially can get rid of this phase. And the way that happens is that this is called a, well, this has to be a topological quantum field theory, but we want it to be the trivial one. So this is sometimes called a symmetry protected phase. Anyways, so there's many different names for this 5-dimensional theory, but let's just.
So it's not good enough that it's a topological quantum field.
It has to be trivial, actually.
So what do you mean by trivial topological?
Yeah, just so good. So right. So let's just look at this term here. So A is a background gauge field. And so and F is its field strength. So this is just a function. So I don't even need to, I don't even need any quantum dynamics in the bulk in this 5-dimensional theory at all. I can just say I take the theory whose partition function is just this number. And that's what I mean by a trivial theory. This is another way of saying a classical theory.
But you're cancelling a quantum one-loop anomaly, right, by classical term, right?
Yes.
And that keeps working if the one-loop anomaly is inside the two-loop, you still get, I mean, this term will still cancel that one, I mean, it works order by order.
Yes. Yes, it is. Yeah. Yeah. Yes.
And this is still only for U1, right?
This one I wrote down as only for U1, but you could do it for any sort of a 12th anomaly. There's always essentially some 5-dimensional trivial phase that you can write down that can cancel the anomaly. Yeah. So we call this the trivial 5D250. It's trivial because there's no operators, there's nothing that's summed over in the path integral. It's literally just a phase. See, if 5D with A is equal to e to the minus ik A F F. And so, since it's a trivial theory, it's scale invariant. So that means that under the renormalization group flow, it just flows to itself. So we can do this exact same trick here, where instead of having z psi where there's some quantum field theory there, we can just say, well, I just literally write down a 5-dimensional theory that has the same property, that it just absorbs this anomaly. And it tells you that anomalies have to be matched between the short distances and long distances, so the UV and the IR, high energies and low energies. And what's more powerful about this the topological quantum field theory perspective is that, as we were just saying, so Atouf's argument only works for this exact type of anomaly. But this can work for any anomalous space. And we'll see that there's actually a very large number of them. And it turns out they all have to be matched because of this sort of argument.
So in this case, for this specific anomaly, these things are completely equivalent.
Yes. Yeah.
It's just a different perspective on the same thing.
Yeah.
We're just saying this generalizes beyond the types.
Yeah, exactly. It works for all dimensions. It works for any possible phase. And there's sort of just, there's a nice recipe. Rather than having to find some theory that's like a conformal theory that has the same anomaly that you can just freely couple to it, or not couple, but multiply it by. You can just say, I just do this, it's way easier. So in a sense they're equivalent, it's just this is more versatile.
Given some M4, can always find a X5 for M4 being the boundary of that, or not? Is it necessary? Or?
That's a great question.
Like, can I just multiply M4 by the real numbers and that will be enough for this argument, or do I need it to be an actual manifold? Like no here?
Yeah, so I think you want it to be an actual manifold. Right. So, yeah, so this picture it's not really a good picture. Because if this goes on for forever, there's actually two boundaries. And so you could have actually two terms here. So really, you need this to be the only boundary. And that's actually sometimes very complicated. And the classification of these are given by some cobordism groups with special structures, and I don't actually know if they're all trivial. So it's possible that there are some anomalies that can't be matched this way. But I don't actually know.
But for simple cases, and for Minkowski space, or for being a sphere or for a sphere, I guess we know manifolds.
Yeah, that's right. Yeah.
Complete in the bulk, right? So
Yes.
I guess for those we're fine.
Yeah, exactly. Cool. Great. Yes,
So you said there being anomalies means that the symmetries realize projectively. What do you mean by that? Projectively where or?
Oh, yeah. Good. So a projective representation. Yeah. So if you have some, say you have a group G, and you want to define a projective representation. So pick some states psi. Say there's I now is a vector index, and G acts on it by some RG, which is essentially a matrix acting on the size. So if you have a true representation, then you would say that R G1 ij R G2 jk is equal to R of G1 G2 ik. This is a kind of a definition. If there's anything that's unclear, I can add more data. So this is a good representation. A projective representation doesn't quite obey this, but it's close. So it's RG1, RG2 is a phase. RG1, G2. And so this is why I made that comment about Berry phases, because this is saying that there's actually some extra phase that's induced by trying to look at how G acts in the Hilbert space, and that there's always extra data in phases when they when it's something non-trivial like this. Yeah. Okay.
So all anomalies have projective representations? Because the structure can be generalized clearly.
Yeah, so I don't think I want to say something that's strong. It's a very strong statement. There's a lot of like very interesting anomalies for different symmetries and different dimensions, and they probably all have different realizations.
And I'll just push on the word projective. It's a projective in the sense that you can remove that overall face by embedding it in a higher space or space.
Right. Okay, good. So a representation is, so R is a map from G, the group, into the space of matrices that, of this space. So we'll just call it V. Or I guess we'll call it H. Let's call it H. That's nice. So this is what a good representation is. Matrices multiply. They obey this sort of thing. A projective representation is when R is a map from G into the projective G, L, H. So when this is a good map. And so essentially this phase comes from the fact that you took an R here and you tried to lift it here. And so you break your associativity. Well, you break this property.
So that defines an anomaly.
I think many anomalies have this property on the open space.
So what is an anomaly?
An anomaly is when the essentially, because you can think of it as either when the when the partition function isn't invariant under a gauge transformation of like a background gauge field, or you can think of it as there is some background you can turn on that breaks your symmetry, that breaks the conservation of your associated current.
And the anomaly is associated with that specific background. So,
so the background you want to turn on, so in order to probe anomalies, I'm only allowing you to turn on backgrounds that are like coupled to a symmetry. So like a background magnetic flux, for example. Then you would say that the anomaly is activated by this flux, but the anomaly is of the symmetry, because I was only allowing you to turn on, it's just terminology.
okay, so an anomaly is a symmetry that breaks under turning on a background field.
Yep.
Okay.
But it's already there, right?
So this is like a way you could diagnose it.
But it's also there without the background, this anomaly. That was what you were saying about either the currents.
That's true too. So you can also diagnose the anomaly by looking at these correlation functions. But it's I think they're actually one and the same, because like inserting a current is the same thing as turning on a delta function source. So
Right. So in the absence of the background, the symmetry is fine. But you're saying, okay, well, you can compute there's something else you can compute in the theory that will show you this anomaly.
yeah. So like when you do when you compute the partition function, you're summing over all states, and that knows that the symmetry is not good in every state. The correlation functions that we're looking at are usually in the vacuum state. And so it's like in the vacuum state, you turn on these backgrounds, then you can see that the current is, the current's no longer conserved.
Okay.
But there has to be first symmetry in the classical action or something.
That's right.
So maybe one more question to tie in this discussion on projective representations in the Hilbert space, and the fact that this partition function transforms by a phase.
Yeah.
But those two things are related, right? Can I view that as also manifesting this literally projectiveness of the representation of the symmetry, or is it a bit different?
It's a tiny bit different. It's a tiny bit different. Essentially, this data is not quite the same as that data in terms of like a math.
Okay.
That's essentially why I don't want to say that every anomaly is a projective symmetry.
So we discussed the definition of an anomaly. What is a Hooked anomaly?
Oh yeah, also whenever I say anomaly, essentially, unless I say ABJ anomaly, I'm specifically referring to a total anomaly.
I didn't see the difference between ABJ and Hooked anomaly.
So an ABJ anomaly does not need to be matched. There's no argument that tells you that it needs to be matched along an RG. And so the reason, well, essentially the reason is that these are dynamical fields. And so it's going to be broken just immediately, just by fluctuations of the gauge field. And so,
Okay, so an Hooked anomaly is something that is there along the entire RG flow, but and the other anomalies can come and go as it is.
yeah, that's right. I do want to give you a caveat though, is that one of the sort of great triumphs of the new categorical symmetries is that what I just told you is incorrect. Yeah, my hope is that in the very last lecture, I'll be able to tell you, essentially show you that an ABJ anomaly actually does give you data that you can follow. And sort of what you give up is that you don't have any sort of symmetry group. It's a symmetry category, which will also make precise later. We started a bit late.
Yeah, we have like about
10 minutes or so.
next 10 minutes. Yeah.
Okay, so then maybe in order to make next week, or not next week, sorry, next lecture easy, I'll try to do a really quick math lesson. So, okay, so this is everything, not everything, but this is most of what we know in quantum field theory about global symmetries of the ordinary type. And so tomorrow we're going to talk about symmetries that act on non-local operators. And that has its own whole set of physics and also its own set of math. And so to make notation a lot more compact, I'm going to tell you quickly about differential forms. So differential forms are right like this. So P. So here, P is a non-negative integer, and what it tells you. So I'm going to write this as omega P. So this is my sort of Euclidean space-time. Here P is telling that this is called a P form. And what it means is that omega P you can write out as a P index tensor. So mu1 through mu P, which are x vectors. Okay? Pretty good. So this transforms contravariantly under chordate transformations. So, for example, if you have a 1 form, then under a chordate transformation, x goes to x prime is transformed to mu1 mu prime, or mu d and there's sort of two important things for calculus that we need. So one is, it's called a few things. So one is called the wedge product. So we take some omega alpha, or omega p wedge omega q. This is a P plus Q form. So what it means is that this wedge product tells you that you take all of these indices and you take these indices and you anti-symmetrize all of them. Okay, that's what that operation means. There's also the exterior derivative. Which we often describe as D. And similarly to the wedge product, what you're going to do is you just take this, the derivative and you anti-symmetrize it. So this is a P plus 1 form, and in coordinates, it's, I guess you would write it as partial mu, mu 1 over mu p, and anti-symmetrize it. And what's important about this is that d squared is 0 always. So by d squared I mean d times d. Okay, there's also an operation called the Hodge star. So this depends on the metric. And so it takes a P form to a D minus D form. And there's a formula that relates the two. So star P U1 through U minus P is square root of G over minus P factorial epsilon U1 through mu P U1 through okay, so this is pretty much all just introduced notation. But there's a reason why this is actually useful. And the reason is that it gives you the most concise version of the generalized Gauss. Stokes theorem, thank you. So, good. So the reason why people even talk about differential forms is that they're naturally the things you actually integrate. So, for example, a 1 form, which I was telling you you can think of as some sort of tensor, this is actually it's not exactly true. You can associate to it a 1 form, or to a degree 1 tensor, but really it's equal to the tensor contracted into the unit length form. And this is coordinate independent. And that's sort of why this is so powerful. And more generally, a P form, and again I said you have this tensor, but you also have this, but really what it is contracted, but it's contracted into this volume form. So this is actually a volume density. And again, this is coordinate independent. So it is literally, it makes sense, it makes coordinate independent sense to integrate differential forms, a differential P form along a P-dimensional manifold. And the reason why volume forms are antisymmetric, it roughly comes down to the d-dimensional analog of the triple product in three-dimensional calculus, or three-dimensional vector calculus. So if you want to figure out the differential volume that's bounded by three vectors, so delta x, delta y, and delta z, so you draw your parallelogram, or parallelepiped, I think, maybe? I don't remember, sorry. So anyways, the volume inside of this differential form is proportional to the triple product, delta x dotted into delta y plus delta z. And as we remember from calculus, this is antisymmetric. Well, it's symmetric under permutation, but it's antisymmetric under pairwise permutation. Similarly, well, that's what it means to do this have an antisymmetric density. So this is why volume densities are antisymmetric, and why P forms are naturally integrated. And so Stokes' theorem, in terms of differential forms, is literally just the derivative of omega p on some p plus one-dimensional manifold is equal to omega p on the boundary, integrated on the boundary of this manifold. And yeah, okay. There's one last concept that I'll probably use, but I'll also probably re-explain again later, is the idea of cohomology. So, so I told you that d squared of omega is identical to 0. And so it's an interesting question to classify when d of omega is equal to 0. And are all of the solutions to this equation given by d of something else? And the answer is no. And the solution here, so essentially the set of all omega, such that d omega is equal to 0, and omega is not the derivative of something else, called P, is called the P cohomology group of the manifold drum. In general, it's actually called the Durand cohomology, but we won't worry about this subscript. And so this is important because it actually tells you about the topology of N. And that's cool, but what's actually going to be more important for us is that we're going to apply the fact that this tells you about the topology of manifolds to the fact that you can apply it to topologically protected gauge field configurations. So for example, if you want to talk about instantons, or if you want to talk about generalized symmetries, it's going to be in this language of cohomology, which we'll probably just talk about in more detail later. But this is definitely a good place to stop in my time. So, thank you.
Okay, so lunch should be served around now. So let's see if it actually is served.